Okay, so let's talk about the physics concepts of work and kinetic energy. We'll have to be a little bit careful in this chapter because we're going to use words like work, energy, and power, which are words we use in everyday life. And here we're going to have precise physics definitions of these words, which may be a little bit different than how you normally use them. Right? You may say, I went to work or I worked hard on this. We're going to have a physics definition. So in the picture here, we have a group of students pushing a bus. In the physics definition of work, it doesn't matter how hard they're pushing, if that bus isn't moving, they're not doing any work. All right, so this is an example of how this word is going to be a little bit different than maybe your everyday use of that word. So let's do an introduction here. Again, the topics that we're going to discuss here are work, energy, and power. Work is kind of a bridge concept. Work is going to take us from things we've learned previously, like force and force problems, and connect us to new ways of solving problems like energy and energy conservation. So work will be the bridge between those two concepts. Why do we do this? Again, because in defining work, energy, and power, we're going to improve our problem-solving toolkit. It's going to be new ways to solve problems. In some cases, these methods are going to be easier than old methods that we've used, like force. In some ways, it may make some problems that we couldn't solve before possible to solve. So this is going to be an important tool for you in solving problems in physics. So let's start with the topic of work. Work, again, is something that we define because it makes problems easier to solve. We're going to have two general equations for work. They're equivalent. We'll talk about why we define two of them in a moment. But here are the two equations. In yellow, we have the differential form of the equation. And in orange, we have the integral form of the equation. Right, so we'll spend the next few slides trying to understand these. I know they look a little bit confusing at first. I think as an undergraduate, I was probably a little bit confused about these at first. And so we're going to try to understand these in a few ways. First, we'll explain them in words and with diagrams. Then we'll expand the equations and write them in a non-compact form. And by doing so, we will hopefully get rid of some of the kind of mathematical symbols here, and it'll make these equations more easy to understand. And then we'll solve it for two special cases. In the case of a constant force, work becomes a lot easier to understand because it's really easy to integrate something that's a constant. And then the other special case is if you just have one-dimensional motion and you have a changing force. So in that case, since you don't have to deal with moving in x, y, and z, and we could say we're just moving in x, it's going to be a lot easier to solve these. So let's go ahead and try to understand these further. As a quick reminder, a few chapters ago, we defined the displacement vector. Right? In 2 dimensions or 3 dimensions, a displacement vector we denote with a delta r to denote a change in our position vector, and it's equal to a change in our x position, I hat, plus a change in our y position, j hat, plus a change in our z position, k hat. So if I start at this solid red dot and I move to this open red dot, I've gone through this displacement. This is my displacement vector, and it has components equal to my change in x in the x direction and my change in y, in this case in the minus y direction. So we define this displacement vector, and then, for example, we use this to define concepts like average velocity in 3 dimensions. It's just displacement over time. Okay, so we're going to use this concept of displacement a lot in this chapter, so I want to make sure we remind ourselves of what this is. We're also going to define something new. It's called a differential displacement, dr, or an infinitesimal displacement, an infinitesimally small step. So dr is equal to dx I hat plus dy j hat plus dz k hat. So if I'm traveling along some path, dr is just a tiny, infinitely small step along that path. And it has components, dx, which is a tiny step in x, dy, which is a tiny step in y, and dz, which is a tiny step in z. Right, so for example, if I moved again from the red dot to the white dot, I would make all these tiny little dr steps along my path. I mean, I could integrate all those little steps to understand my full displacement, for example. So we need to define this in order to understand our definition of work. Okay, so let's look at our definition of work. Let's first look at the differential form. dw is equal to f dot dr. Okay, so let's try to understand this first by explaining it in words. For an object moving a tiny step dr, which is an infinitesimal displacement along some path, the scalar quantity defined by the scalar product of the force vector f and the infinitesimal displacement vector dr is equal to the work done dw by that force during that small step. All right, so that was a lot, and we'll explain this more on the next slide. dW is a small change in our work, and it's equal to our force dotted with our small step dr. Okay, but again, let's try to explain this in different words, a little bit less mathematical. So in other words, work is something that can be done by a force, and for work to be done, the object has to move. There must be displacement. So dr is a small step. You must be making some small step. You must be having some displacement. And b, for work to be done, a component of the force must point parallel or antiparallel to the displacement direction, and therefore increase or decrease the velocity of the object. Right? So let's try to explain this a little bit more. As I move from point A to point B along this path, say I'm at this location at this time, and I'm making some tiny step dr in this direction at that moment, right? And say at that moment there's a force pushing on me, which is this force, right? Well, I'm moving in this direction, and the force is pushing in this direction. So it's only a component of that force which is kind of helping me move along that direction, or going to be speeding up my progress along that direction. And so if I look at this, the F cosine of theta is going to be the component of the force along this dr direction, the component parallel to that small step. And that's exactly what this dot product is doing. It's a mathematical way of determining how much of this force is parallel to this displacement. Right? So we're figuring out how much of the force is parallel to our displacement. Then we multiply that component of the force, which is parallel to displacement, by the displacement, and that's what our work definition is. Okay? Let's do this again with a little bit of an example. Let's say, again, we're traveling along this path, and let's say, in this case, it's a sailboat, which is traveling on this path along in the lake. And let's say the wind is constantly blowing in this direction, okay? So I start off, I'm traveling along this path, so my displacement along, for the first second of my motion is in this direction as I travel along that path, and the force is in this direction. So the force and the displacement are pretty close to parallel. So most of that wind force is going to be helping me move, right? So in this step, this corresponds to a lot of work being done during that step. Where in this step, again, the force is pointing at, maybe 60 degrees away from the direction I'm actually traveling, right? So in this case, a lot of that force is not that useful to me. It's only the component of the force which is parallel to my displacement, which is going to be useful work, which is going to help speed up the sailboat. Okay, so the work at this step is going to be smaller than the work at this step because the force is less aligned with our displacement. Okay, so I hope that helps us to understand conceptually what is work. We can talk about this more with a couple examples, with these dog examples. So we've got these three different examples of dogs doing something, and the question is, are they doing work using the physics definition? Okay, so in the first example, case A, we have a skateboarder with a dog pulling the skateboarder. Right, so there's a force of tension of the dog on the skateboarder, and that tension force is this blue force along the leash towards the dog. And that tension force has two components. It has a tension in the x direction, which is parallel to the direction that the skateboarder was traveling, and it has this t sub y in the minus y direction. And it's got tension, which is kind of pulling this person's hand down, but the person is kind of resisting that, right? So that hand isn't actually moving down. The skateboarder as a whole is moving in this direction. He has displacement to the right in the x direction. And so looking at this situation, this dog is doing work, right? The force of the dog on the skateboarder is doing work, but it's only the x component of that tension force which is doing work, right? That x component is parallel to the displacement. The x component is going to help move the skateboarder along. It's going to cause acceleration, for example, in the x direction. This component of the tension in the y direction is not doing any work. It's not helping to make the skateboarder move. It's not resulting in any displacement. It's not aligned with the displacement direction. So that component of the tension is kind of wasted, right? It's not helping to speed up this skateboarder. All right, so that's our first example. In this case, the dog is doing work because an x component of the tension is parallel to the displacement. Let's look at case B. In case B, we have a dog holding an umbrella at rest. So we can draw a free body diagram, for example. There's the force of the dog on the umbrella upwards, and the force of gravity on the umbrella down, right? So the dog is holding up this umbrella. But by our physics definition, this dog is doing no work, right? Because in our definition of work, it involves displacement, or in this case, our displacement differential, a small step in some direction. Right? This dog is not moving, there's no displacement, so he's doing zero work. So yes, it may seem, maybe that's a heavy umbrella, and it may seem like that dog could be really straining to hold that umbrella up, but by our physics definition, the dog is not doing any work. And in the last case, case C, we have this puppy carrying a bowl, and the puppy is moving, the puppy is walking. So that bowl is undergoing some displacement. The bowl is moving in the plus x direction, but all the forces that the puppy is applying to the bowl are in the y direction. We've got the force of the puppy in the bowl upwards, and the force of gravity on the bowl downwards. Right? This puppy is walking at a constant speed. The only forces on the bowl are in the y direction. And so in this case, even though there is displacement and the puppy is applying a force to the bowl, the puppy is still doing no work by our physics definition, because the force of the puppy on the bowl is perpendicular to the displacement. Okay, that force that the puppy is applying to the bowl is not helping to, for example, speed up the bowl. So that puppy is doing no work. Okay, that was a silly example, but I hope it helps. Okay, so that was our differential equation for differential form of our work equation. Now let's talk about the integral form. So as we move along this path, we could figure out for each tiny little step how much work was being done for that tiny step using our differential form of the equation. And so if we wanted to figure out the total work done along this entire path by this force, we would just integrate that differential form, right? If we know how much work is done during some tiny step, we can integrate this along this path, and that becomes our integral form of work. So as we move from point 1 to point 2, or in this case, point A to point B, this equation is the integral from point 1 to point 2 of f dot dr. Okay, so let's understand this in words. For an object moving from point A to point B, work is a scalar quantity defined by the line integral along the path from A to B of the scalar product or dot product of the force vector and an infinitesimal displacement vector. Okay, so explaining it out in words may help a little bit, but I think it may be more beneficial to expand this equation out. Again, we typically are going to write physics equations in as compact a form as possible. Physicists are lazy, they won't like to write things without writing very much, right? So we're going to write this in a very compact form, but I think it'd be helpful to expand this out and help to understand it better. So let's do that. Let's look at what is f. Well, f is a force vector, so it's something that could have an x component, a y component, and a z component, and we keep these components separate by using our unit vectors, I hat, j hat, and k hat. So this is a three-dimensional force vector. What is dr? Right, this is our differential displacement. It's a small step in x I hat plus a small step in y j hat plus a small step in z k hat. Right, so this is just keeping separate our x, y, and z displacements. Okay. What about the dot product? The dot product we have an equation for, we're familiar with. The dot product between two vectors is equal to the magnitude of A times the magnitude of B times the cosine of the angle between those two vectors. And it's also equal to the x component of A times the x component of B plus the y component of A times the y component of B plus the z component of A times the z component of B. Right, we've seen that before from chapter 2. So, okay, we have our dot product definition, and we know that a dot product, you put in two vectors and you get out a scalar, right? These are both equations for numbers, not vectors, okay? And so with these three pieces of information, we can write this out in an expanded way. So let's do that here. So f dot dr, well, I could use this definition for my dot product and write f dot dr as just the magnitude of my force times the cosine of the angle between my force and my displacement times dr, right, times my small step, magnitude of my small step. So that's one way we could write this out in integral form. We could also use this definition of a dot product to write this out, and it becomes just the integral, and instead of from point 1 to point 2, in the x direction, we're just traveling from x1, x2. We're traveling some distance along x, and we're integrating the force as a function of distance. And then we do the same thing in the y direction and the same thing in the z direction. So to me, this is the most easy form of the equation to understand. In the x direction, we're going to integrate the x component of the force as a function of position. In the y direction, we're going to integrate the y component of the force as a function of our displacement in y, and in z, we're going to integrate the z component of the force as a function of our displacement in z. And we're going to do it along our path z1 to z2, for example. How far are we moving in the z direction? And so I find this to be somewhat easier to understand. Okay, so now that we wrote that out, we can now use that kind of expanded equation to understand a special case of a constant force. If we had a constant force, and let's just look at the x direction, for example, we could look at the equation we just derived for the x component of the work, which is the integral from x1 to x2 of the x component of the force as a function of our x here. If our force is constant, we can just pull it out of the integral. And then I'm just integrating dx. Integral of dx is just x, right? The integral of 1. Integral of 1 is x. And we evaluate that from x1 to x2. And so this is just force times x2 minus x1. And this is our definition of displacement in x. Right? My final position minus my initial position. So in the end, we get force times displacement. Okay, and so we could do that in x, y, and z, and we get this equation for work, which is only true in the case of a constant force. This isn't generally true. It's true only when we have a constant force, but if we do have a constant force, if we're using gravity near the surface of the Earth or something like that, the work equation becomes much more simple. I just need to know the x component of my force and multiply it by how far am I traveling in x. Then add to that my y component of the force and multiply that by how far am I traveling in y. And then multiply the z component of my force times my displacement in z. Right? So that's a lot easier to understand. Um, or we could also write this in terms of the other form of our dot product, which is I multiply my force times my displacement, just how far am I traveling, and then I multiply that by the angle between the force and my displacement. Okay, and so this is also a really good conceptual idea to have in your head. If the angle between these two things is 0, cosine of 0 is 1, and I'm doing the most possible work. If the cosine is 45 degrees, cosine of 45 degrees is some number less than 1, so I'm doing less work. If this angle between the force and displacement is 90 degrees, I'm doing 0 work, because cosine of 90 degrees is 0. Okay, so both of these can conceptually help you to understand the concept of work. And this may be a good opportunity to make a quick note about the units involved in work. First of all, work is a scalar. It's a number, not a vector, right? So our equation for work is going to return, either of these is going to return just a number. It has no direction. And for the unit of work, we're going to define a new unit called the joule. Okay, so we look at what work is contained of. Work is force times distance, so that's newtons times meters. And that's also a totally okay unit for work. So if you report your answer for work in terms of newton meters, that's totally fine. But we can also say, what is a newton? A newton is a unit of force, so it's mass times acceleration. So that's kilograms times meters per second squared, and then times our meters. And so we get kilogram meter squared per second squared, which is our definition of a joule. All right, so joule is going to be our unit of work. Okay, now that we know that, we can keep going here and try to understand work a little bit better. So we're talking about the special case of work with a constant force, and now let's think about the most simple case, which is force in the same direction as the displacement. So we've got a box on the floor, and we're moving it in the x direction. We have some displacement in x, and we're pushing it only in the x direction. In this case, if we look at our work equation for a constant force, well, I have no force in y, I have no force in z, so that's 0, that's 0. I'm only pushing in x. And then I also have no displacement in y or z, right? So this is 0 and this is 0. So in this case, since I'm only applying a force on x and I'm only moving in x, my equation for work becomes really simple. It's just force times displacement, right? So that's our most kind of fundamental conceptual understanding of work, is we're multiplying the force by how far are we moving, okay? And so the work done by this person as he pushes this box is just force times displacement. If you push it twice as far, you're doing double the amount of work, okay? And so that's our most simple case. But let's try to understand slightly more complicated cases. Let's say your car is stuck in the snow and you're trying to push the car out, all right? So these three people are pushing on this car, but look at this guy. This guy's got his hand in the pocket, number one, and number two, he's pushing on the car at an angle, right, where these people are pushing on the car kind of straight. So let's talk about the work done by this guy. Let's say the car is traveling in this direction, say in the x direction, but you're pushing on the car at an angle, okay? How much work do you do in this case? Well, let's use this equation. It's a constant force, so we can use our constant force equation for work. And let's just plug in for all of these different variables. To understand this a little bit further, again, we're pushing at some angle, so we have a component of that force which is in the x direction, which is aligned with our displacement, and a component which is in the y direction, which is not aligned with our displacement at all. It's perpendicular to that. So using our definition of work that we have down here, I can write it out like this: f of x delta x plus f of y delta y. The x component of my force is just my force cosine theta, because that's adjacent to, this component is adjacent to this angle, right? And my y component of the force is f sine of theta, so that's okay, that's opposite that angle. But I'm only moving an x, so my displacement in y is just 0, right? So this term goes away, and so the work done by this person as he's pushing the car is the force he's applying times the displacement of the car, but multiplied by the cosine of the angle that he's pushing at, right? So if he was pushing at 0 degrees again, he would be doing maximum work because cosine of 0 is 1. But he's pushing at some angle, so it's going to be some number less than 1. So some of his force is kind of being wasted. It's not being useful here, right? So what matters is how aligned is the force with the displacement, right? In this case, his force has only this small component which is aligned with the displacement, so it's only this part of the force which is doing work, right? This component of the force is not doing work, okay? So this equation handles that case where your force is not in the same direction as your displacement, right? The cosine in this equation handles that for you, but also writing out in this way with thinking about the x and the y component separately will handle that situation for you. Okay, so let's talk about whether work can be positive, negative, or 0. What is positive work? Positive work is when the force has a component which points in the same direction as the displacement, right? So in this case, we could be moving in the plus x direction, so we have positive displacement, and it could be pushing at an angle, but a component of the force is also in the positive direction. So when I calculate the work done, again, like we did in the previous slide, there's no displacement in y, so this term goes to 0. Work is just the x component of the force times displacement, and if the x component of the force is positive and the displacement is positive, the work must be positive. We're doing positive work. What if the car is traveling in the minus x direction? In this case, I have negative displacement, but I'd also be pushing, in this case, at this angle, and so a component of my force would be pushing in the negative direction also. So using my work equation we just derived, I now have a negative component of my force and a negative displacement, so negative times a negative is a positive. So both of these are examples of positive work. So it doesn't matter if you're traveling in the plus x direction or the minus x direction. What matters is that a component of your force is aligned with the displacement. Okay? What about negative work? Negative work is when your force has a component which is opposite the direction of your displacement. So say the car is sliding down a hill in the plus x direction, you have positive displacement, and you're at the front of the car trying to stop it from moving. So you're pushing on the hood of the car, and let's just say we're pushing at this angle for some reason. A component of your force is in the minus x direction. Okay, so I have now positive displacement, but I have a negative force. So that means negative work. So negative work is when your force is opposite the direction of your displacement. Likewise, I could be moving in the minus x direction. I could be sliding down the hill in the minus x direction and applying a force which has a component in the positive x direction. In this case, I have a positive force and negative displacement. That's negative work. Okay? And finally, 0 work, which we've already mentioned. If the car was moving in the plus x direction, it's sliding down the hill, for example, in the plus x direction, but you're pushing on the side of the car, you're not really helping. You're not going to stop the car, you're not going to speed up the car, you're not going to do anything to the car. You're doing 0 work, right? So in this case, if we use our work equation, my component of the force in the x direction is 0, so this term goes to 0. my displacement in the y direction is 0, right? This car is only moving in x. So this term goes to 0, and so I'm doing 0 work. So using this equation for work, if my force is perpendicular to my displacement, I'm doing 0 work. Okay, I'd get the same answer if I was using the cosine definition, because cosine of 90 degrees is 0, right? And that angle theta is the angle between the force and the displacement. Okay, one last note on whether work is positive or negative. We have to be somewhat careful about what object we're talking about. So let's use the example of a weightlifter lowering a barbell to the floor. So we have this displacement, and say we define plus y to be up, we have some negative displacement here. Whether this weightlifter is doing positive or negative work, well, we have to be careful about what object we're talking about, and so I really encourage you to draw free body diagrams for every object in the problem, just like you would for a fourth problem. And so let's take a look at that. I'm not drawing a full free body diagram here, but let's just quickly look at the objects involved. Let's talk about if we're considering the force of the hands on the barbell. The hands are pushing up on the barbell even though he's lowering it to the ground, right? He's still stopping it from falling. He's still pushing up on the barbell. So we have a force in the plus y direction, but displacement, which is negative, so that's negative work. The weightlifter is doing negative work. His force is anti-aligned with the displacement. Okay, he's doing negative work. But if I think about the barbell, the force of the barbell on the hands is down, right? If you're holding out your hands and the heavy barbell was in your hands, the barbell would be pushing down on your hands, right? And so the force of the barbell on the hands is down, so the barbell is doing positive work here. The barbell is moving down, the barbell is pushing down on your hands, and your hands are moving down. So the barbell is doing positive work on your hands. We need to, just like we did when drawing free body diagrams, be really careful about what objects are involved and which forces are applied to which objects. And here we have a Newton's third law pair, the force of the hands on the barbell, the force of the barbell on the hands. Just kind of a reminder, be sure to specify what object you're talking about and which forces are doing work on what objects when you're calculating work. Okay. In the next video, we'll talk about work for varying forces instead of constant forces.